Hello, so this is video number 2 of section 6.5. And so just a quick note, after this for today's lectures, so following the schedule, today is Thursday, July 2nd. There's one video for section 6.6 after this. So sticking to the sort of at most generally 3 videos schedule, but this section has 2 videos and the next section will have 1. So I've got another least squares problem on the board behind me. But today I want to, this lecture, I guess, I want to briefly discuss a couple of ways we can solve or find a least squares solution to the matrix equation AX equals B as an alternative to solving the equation A transpose A x hat equals A transpose B, which we used last time. And so here, remember, we sort of started this out in last video by noting that the vector B hat we're looking for, right, which is ultimately the best approximation to B given the columns of A or given the column space of A, is just this orthogonal projection of B onto the column space of A. And so remember last time I had said the traditional or methods we had introduced early in this chapter of just directly calculating this vector would end up taking us quite a long time if the columns of A weren't already orthogonal. But if the columns of A are already orthogonal, then calculating this vector B and then later this vector x hat tends to not be so involved. So if the columns of A are already orthogonal, directly calculate B hat. And so notice in this example, column 1 of A, so in this example, if A1 is equal to the column vector 1, 3, negative 2, and A2 is equal to 5, 1, 4, then A1 dot A2 is verifiable will be 0, 5 plus 3 minus 8. And so we set A1, A2 is an orthogonal basis for the column space of A. And so remember, this last sentence here was the roadblock we had talked about last video to just directly calculating this in the normal way we knew how to, right? The ways we learned to calculate this relied on having an orthogonal basis. And as you remember from doing the Gram-Schmidt process in section 6.4, starting with a non-orthogonal basis and finding an orthogonal basis was definitely way more work than doing the A transpose A trick that we introduced last video. But given that the columns of A are orthogonal, you'll see that this process is not going to be terribly hard. So since the columns of A are orthogonal, like we said, we know that B hat, which is the best approximation to B using the columns of A, which is just the orthogonal projection onto the column space of A of B, is equal to B minus A1 dot B over A1 dot A1 times the vector a1 minus a2 dot b over a2 dot a2 times the vector a2. And so notice this just falls in line with the definition of the orthogonal projection of B onto the column space of A. And so calculating this, we get the vector B, which is 4, -2, -3, minus a1 dot B, which is equal to 4 over a1 dot a1, which is equal to 14, times 1, 3, -2, minus a2 dot b, which is equal to 6, over a2 dot a2, which is equal to 42, times the vector 5, 1, 4. So now, distributing these two fractions and doing all of this vector arithmetic, you should get that b hat is equal to 1, 1, 0. So, we're not quite done yet, right? Because ultimately we want not only b hat, right, which is the best approximation to b using the columns of A, but we want the vector x hat, which is doing the approximating. So we're kind of doing this in a slightly different order than we did the previous problem, right, where here now we're going to solve the matrix equation A times x hat is equal to b hat, since we now know what b hat is. And so solving this amounts to solving this matrix equation. And so remember, we want to row reduce the corresponding augmented matrix. Feels like it's been a while since we've had to call on our row reducing skills, but doing this, you should get that the least squares solution x hat, which is equal to the variable x1 hat, x2 hat, should be equal to 2/7, 1/7. So this is the least squares solution, and this is our approximation to B using the columns of A, where again, sort of x hat is this vector defining how we're going to combine the columns of A to approximate B. So one sort of different way of approaching this, I think if you can tell the columns of A are orthogonal right off the bat, generally that's fairly easy to check if A has 2 or at most 3 columns. This way tends to be a little shorter, right? These two fractions aren't terribly hard to calculate. You don't have to do tons of matrix multiplication, and then generally you're left with an easy solution at the end. But certainly, again, the A transpose A method is just as valid. And actually, if you go back to video 1, I had mentioned there was something funny about the example I chose. And if you go back and look at the matrix from the last example I chose, that matrix actually also had orthogonal columns. So if you want more practice with this method, you should go back to video 1 and try finding the least squares solution in that example, but using this method instead. So there's one more way that we can find least squares solutions. And I'd say I'd probably never recommend doing this way by hand. It's kind of funny because, so I'll state the theorem and then we'll start the example. Your book recommends this because this can be useful for minimizing errors in calculations. But as you'll see, I would feel like this sort of process would, at least doing this by hand, tend to maximize the amount of errors one would make in calculations. So this might be useful if you're using computer software to help you do this. Matrix A with linearly independent columns. We're going to let A equal Q times R be a QR factorization. For A. Then for each vector B in Rm, the least squares solution, and notice here we know it's unique because A has linearly independent columns. So if we have a QR factorization of a matrix, then we can find the least square solution like so. Basically, this is just sort of rewriting our QR factorization, sort of rearranging it. Again, for this, I won't go too in depth with a proof. This is theorem 15, like I said, in section 6.5 of your book, if you're interested of a proof of this fact. So I think the reasons for this, or maybe one reason for this, I think what your book says is that I think if you have like a small error in how you calculated your QR factorization, then this method sort of is going to minimize the magnitude of the errors you might make. So if you were to make an arithmetic error, this method of finding the least square solutions might minimize that error. I also think that much like with the previous matrix factorizations we looked at, that this could help if we had to find many least square solutions to many matrix equations with the same matrix A, right? Because notice, let's say we had, 100. Hold on, let me finish writing up the problem here. So suppose that we had like 100 vectors B, and we wanted to find the solution in that case that we had 100 vectors B, right? One QR factorization, while it takes long, definitely by hand, I mean, certainly a computer could do it in a relatively easy amount of time, but one QR factorization by hand, while it takes long, right? Once we have R inverse and Q transpose, all this amounts to then is the multiplication of two matrices and a vector, right? Whereas the other two solutions to these least squares problems that I had introduced always involve solving a matrix equation of some sort at the end. And so that will always involve doing some amount of like row reducing or or multiplying by an inverse or something, and so or calculating an inverse, right, which eventually involves row reducing. And so certainly if you can do this one-time QR factorization calculation, then over the long run of finding least squares solutions to many, 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 many matrix equations, this might start to take less time. So I would feel like this would be the much more sort of applicable reason as to why we introduce this method for finding a least squares solution, because certainly if you're doing it for a single problem by hand, I would never recommend doing it this way. But so I figured it couldn't hurt to get one more practice problem doing a QR factorization. So to finish this video, we're going to work through this last problem where we find a QR factorization of A, and we're going to use it to find a least squares solution to the matrix equation AX equals B, if B is the following vector. So QR factorization, the first thing we want is an orthogonal basis V1, V2 for the column space of A. And so remember, to do that, we're going to use the Gram-Schmidt process. And so remember, the Gram-Schmidt process tells us that V1, and actually I think to save space, I'm going to go ahead and erase the board here just to make sure we have room. So the problem is outlined on the worksheet, and certainly a few seconds earlier in this video. So the matrix A was 2, 2, 1, 3, 4, 1. So first step, we're going to let A1 and A2 be the columns of A. And so notice these two columns are linearly independent. And so A1 and A2 together form a basis for the column space of A. But to find a QR factorization for A, we need an orthogonal and then an orthonormal basis for the column space of A. So using Gram-Schmidt, to find an orthogonal basis, which we'll call V1, V2, for the column space of A. So remember, Gram-Schmidt tells us, well, maybe the first vector I take, V1, is just equal to the first vector in the original basis. Maybe my favorite step of the Gram-Schmidt process. Unfortunately, finding V2 is a little more challenging. So remember, this is equal to the second vector A2 minus the orthogonal projection of A2 onto V1. So we calculate a few dot products, but that's okay. So working all of this out, we get that V2 is equal to 3, 4, 1. A2.V1 is equal to 6 plus 8 plus 1, so 15, over A1.A1, which is equal to 9. Keep that in mind because we'll need to call on A1.A1 again later on, times the vector A1.A1. Working out these fractions and doing some arithmetic, I got that V2 is equal to 1/3, 2/3, negative 2/3. All right, so the next process in the the next thing to do in finding a QR factorization for A is to normalize this orthogonal basis, V1, V2. So right off the bat, so now we want to find an orthonormal basis for for the column space of A. And this is a little easier because we just have to normalize the two vectors v1 and v2. Well, so the norm of v1, remember, is the square root of v1 dot v1. We already calculated the square root of v1 dot v1 to be 9, and the square root of 9 is just equal to 3. So u1 will equal 2/3, 2/3, 1/3, and u2, well, notice that 1/3 squared plus 2/3 squared plus 2/3 squared is actually equal to 9 over 9. And so the length of v2 is already equal to 1. And so we actually already have our orthonormal basis for the column space of A, which is the vector 2/3, 2/3, 1/3, and negative 1/3, 2/3, negative 2/3. And so I'll save Q over here. Our matrix Q in the QR factorization of A is 2/3, 2/3, 1/3, negative 1/3, 2/3, negative 2/3. All right, so step one in the somehow process your book recommends to minimize errors. I don't like all those fractions. I feel like fractions are just calling, at least for me, fractions are just like a calling for me to make errors. So, all right. So now remember, R in our QR factorization is a little easier to find than Q because R is just equal to Q transpose times A. So Q transpose is the matrix 2/3, 2/3, 1/3, negative 1/3, 2/3, negative 2/3 times A. And so doing the matrix multiplication dance a few times, I actually got that R wasn't quite as scary of a matrix as Q was. And this makes sense, remember, because R should be an upper triangular matrix with positive entries on the diagonal. So we have our QR factorization for A. So now remember what theorem 15 tells us is that a least squares solution, x hat, where remember B is the vector 7, 3, 1, and we want a least squares solution to x equals B. And so remember, theorem 15 tells us that a least squares solution is equal to, let me make sure, R inverse times Q transpose times B. And so we're not quite done because we need to calculate R inverse. Well, this is just equal to 1 over the determinant of R times 1, negative 5, 0, 3. The determinant of R is equal to 3 times 1 minus 0 times 5, which is 1/3. And so R inverse is equal to 1/3, negative 5/3, 0, 1. And so now that we have every matrix necessary to do this, we get that the least squares solution is equal to R inverse times Q transpose times b and so the order I would do this in I would multiply this matrix times this vector first. The reason is because I noticed that this was going to give me a vector of length 2, so it'll just decrease the amount of calculations I need to do. And so doing the matrix multiplication dance a few times, you should get that this is equal to the following matrix vector product. I got 7, -1. And then multiplying r times that, I got the vector 4, -1, which is a least squares solution to this matrix equation. So 2 more ways to find least squares solutions to matrix equations. As sort of a note, I think in the problems, I think you will be given one of these problems, at least on your homework. In these problems, your book actually starts out by giving you the QR factorization, so that certainly cuts down on a lot of the time. I think I wanted to just go through the QR factorization one more time just to get the practice, since it's kind of an involved process. But again, as you could see, like once we've calculated our inverse, right, if we had to do this then for multiple vectors b, all we would have to do then for the rest of the 99 vectors, if we had like 100 vectors we were trying to do, is this last step. Right? Because at that point, this matrix and this matrix would never change. The only thing changing is this vector. So certainly, if you had to do many of these least square solutions, this method might actually start to be useful. So next video, like I said, we'll move on to section 6.6, where we get to see a really cool application of some of what we've learned.